Another approach for shifting the emphasis in statistical analysis away from the null hypothesis is model testing. For example, depending on where you live, you have probably heard of wind chill temperature, a combination of air temperature and wind speed that describes how cold the air feels. The formula for calculating the wind chill temperature does not perfectly describe the reality of wind chill temperature. It is instead a model of temperature perception, a mathematical formula that predicts our perceived temperature by taking into account two variables, air temperature and wind speed. Denoting the air temperature as T and wind speed as V, the formula for wind chill is as shown here. If the air temperature is 20 degrees Fahrenheit and the wind speed is 10 miles per hour, then we plug those values into the formula and find that the model says the wind chill will be about 9 degrees. But what is the wind chill really? We know that it feels colder when the wind is blowing, but where did this formula come from? Does 20 degrees Fahrenheit really feel like about 9 degrees when the wind is blowing at 10 miles per hour? Not exactly, not necessarily. If it is midday and the sky is clear, then it likely does not really feel like 9 degrees. The formula is only a model, an imperfect description of the reality of temperature perception. That model assumes that sunshine is not a factor, even though bright sunshine can raise the wind chill temperature by 10 degrees or more. Humidity also makes some difference, though not nearly as much as how much sunshine there is. So it might be more accurate to add one more term to the end of the model. In statistics, the fudge factor is called error. Error is simply the difference between the model without the fudge factor and what actually happens. In the case of wind temperature, error is the difference between the model's predicted perception of the air temperature and our actual perception. Another proposed alternative to null hypothesis significance testing methods is to build and improve models of our dependent variables. Like some of the estimation methods, model testing and comparison may depend in part on null hypothesis methods, but the focus is shifted away from the concern with the null hypothesis and toward the development of more precise theories of psychological phenomena. So, if we are interested in temperature perception, then we build a model that includes two variables, temperature and wind speed. If we want or need to improve upon that model, then we may need to include a term in the model for sunlight, making it more complex, but also more accurate. We might then wish to see if we can improve upon the model by adding a term for humidity, but then discover that the model is not much improved, certainly not enough to justify the added complexity. Of course, in psychology, one of the sources of error in prediction is people. One person's perception of temperature may be different from another person's. You might be surprised to learn that the wind chill model was tested on a sample of just 12 people. You might also be surprised to learn that many of the more common statistical tests, such as the t-test, the analysis of variance, and linear regression, all conform to a common model called the General Linear Model, or GLM. In the model-building approach, instead of comparing predictions from GLM or another model to a null hypothesis, those predictions would be compared to the predictions of other models.